In this video, we're going to take a look at the nature of gases, the kinetic theory, gas pressure, and how they relate to each other. So, kinetic theory has to do with kinetic energy, energy due to motion. Anything that is in motion has kinetic energy. And kinetic theory states all particles are in constant motion. Unless they're at absolute zero, 0 Kelvin, all particles are at least vibrating and have some sort of motion going on, giving them some sort of kinetic energy. So the particles in a gas, we consider them to be hard, small spheres that have an insignificant volume. We know atoms actually take up space, but relative to the amount of space that they take up, it's mostly just emptiness between them, but they're moving so fast they appear to occupy all of that space. These gases will spread out and take up the shape and the volume of whatever container they're put in. They will spread out without limit to fill up and occupy as much space as they can. They try and get as far away from each other as possible. They just keep spreading out more and more and more as much as they are allowed. These particles are moving really fast. At room temperature, they're moving 1,700 kilometers an hour, or 472 meters per second, in these straight line paths until they collide with another particle or with a wall or an object that is in their way. And all collisions between particles or the objects which they collide with are considered to be elastic. That means whatever kinetic energy they have when they collide remains as kinetic energy. They're not going to lose any of their velocity, any of their kinetic energy when they collide with these objects, turning into sound or light or heat. They're just going to remain kinetic energy. Here we see two different containers, the same amount of particles, but at different temperatures. The one on the left is a lower temperature than the one on the right, so the particles are moving slower. On the Kelvin temperature scale, there is a direct relationship between how fast they're moving and their temperature. So doubling their temperature on the Kelvin scale will result in roughly a 1.4 times faster velocity for these particles because kinetic energy is 1/2 mv squared. Here we see some gas trapped in the left half of this container, and it's closed off, so it can't get to the right half. But then once that is open, they will spread out and occupy, again, as much space as they can, and it fills up both sides of this container. So the gas pressure is the result of all these particles as they collide with the walls of the container that they are in. And they push against, resulting in a force, and that force over an area gives us a pressure. They're moving around rapidly, colliding multiple times every second with the walls of the container they're in, and that's how we get the pressure that we observe. If there are no particles, then there is no pressure. We call that a vacuum, like in outer space, where there aren't any gas particles for the amount of space really there are. It's so few, it's negligible, so there is no actual pressure in space. The atmospheric pressure is a result of gravity pulling down all the gas that's in our atmosphere down on us, and that pressure we feel as they're colliding with us, and that gives us, again, that atmospheric pressure, which can change with weather systems and with altitude. In weather systems, when you have a high pressure system, that's when you have the nicer weather and clear days. When it's stormy weather, that's a low pressure system. Also, as you change in altitude, as you go higher in altitude, since there's less gas above you being pulled down, then you have less atmospheric pressure. And as you go down in altitude, or go even like below sea level, like in Death Valley, where there's more gas particles above pushing down you, then you have a greater amount of atmospheric pressure. So here we see a football, the ball on the left having 12 psi because of the amount of gas particles in there as they're moving around and colliding with the walls of the football. And then in the middle where we pump it up, we put more gas particles in. And now since there's more gas particles, more collisions, more pressure. And then on the right, there's less gas particles, the ball's deflated. And since there's less particles moving around and less collisions happening, we end up with lower pressure. So the atmospheric pressure we just discussed can be measured what we call a barometer, the barometric pressure. It's a device, again, that we use to measure the atmospheric pressure. And the SI unit for pressure is a Pascal. But like grams, they're really small. So we usually talk about terms of pressure as far as pascals, but actually kilopascals. And we can also use millimeters of mercury and atmospheres. And again, as we saw in the previous slide, also PSI, but that's only an English unit, not a metric unit. So the relationship between these three units of measurement is 1 atmosphere of pressure is 101.3 kilopascals is also 760 millimeters of mercury. And since those are all equivalent to each other, we can use those as conversion factors, as we'll see in a second, to get between the different sets of units of pressure. And so standard pressure is when you have 1 atmosphere of pressure and 0 degrees Celsius. That's STP. As we discussed with that 22.4 liters of gas at STP, again, that is a set of conditions with 1 atmosphere of pressure and 0 degrees Celsius. So here we see how a barometer works. It's open, so the gas particles in the air can be pushed down on top of the mercury, as we see there in the bottom of that container. And then inside that tube, all the air is sucked out, so that way that mercury can move up and down that tube without there being pressure being built up as that changes. And so the more that the atmosphere pushes down on the surface of the mercury inside the container, the more it forces it up that tube, and you can measure the amount of pressure that is therefore being exerted on the outside. So here's one of these conversions between different pressure units. So let's say we have 125 kilopascals of pressure. How many atmospheres is that? Also, how many millimeters of mercury? Again, since I had those different equivalencies between those different pressures, then I can use those as conversion factors. So we'll list out what we know and what we don't know. We do know that we have 125 kilopascals of pressure, but we don't know how many atmospheres that is and how many millimeters of mercury that is. But again, if we were to take those three equivalencies from the slide prior, 101.3 kPa is equal to 1 atmosphere is equal to 760 millimeters of mercury. Again, I can use those as my conversion factors. So I'm going to take my given and put it over 1. So 125 kPa over 1. If I'm trying to get to atmospheres, I need a conversion factor that will get rid of those kilopascals. So I want to reduce out kilopascals and get to atmospheres. So I'm going to say 1 atmosphere is 101.3 kPa, so those kPa will reduce out because anything divided by itself is 1. And I find there to be 1.23 atmospheres of pressure. And I can do the same thing for millimeters of mercury. I'm going to take my 125 kPa, put it over 1, and then now this time put 760 millimeters of mercury over that 101.3 kPa. So again, kPa reduces out, but now I get millimeters of mercury, not atmospheres, and then I solve it out and find that there are 938 millimeters of mercury for 125 kilopascals. So kinetic energy and temperature, how are they related? Temperature is the measure of the average kinetic energy for any given substance. Again, that kinetic energy, as we discussed, is 1/2 mv squared, mass times velocity squared. Since it's the energy due to motion, velocity is going to be a part of that component. Particles can have a small range or a wide range of energies. So to get an average, again, you're going to take up all the particles and add them together and divide by their total. So I can end up with an average of 10 if I had 3 different particles that had a velocity, say, of 9, 10, and 11, but I would get the same average if they were 5, 10, and 15. The average would be 10 in both cases. So I can have a wide range or a small range and end up with the same exact average. But as I heat up a substance, that range is going to get larger. The amount of energy that is going to be between the lowest and the highest particles of that substance is going to be more greatly different as you heat up a substance. And particles will absorb energy. As you put energy in, they'll absorb it, and it'll move faster and faster and faster, and they will speed up. And then that temperature, again, when it is on the Kelvin scale, is directly proportional to its kinetic energy. So doubling the amount of kinetic energy will double the temperature, again, on the Kelvin scale.